Hi, Introduction to Bacteriology and Staphylococcus species. What are bacteria? They are single-cell organisms. They are very small, tiny. That's why term microorganisms, micro. Need the microscope to see. Can be found on most material and surfaces. Here you can see some electron microscopic pictures. So famous microbes, E. coli O157X7. It's a colored one. It's a black and white one. You can see but it's electron microscope, but it's not commonly used for identification of the microbes. So what do they look like? It's the morphology. There are three basic shapes. Rod shape. The one is round shape or cocci. Rod shape beta rods or bacilli. And there another one is called spiral shape. Other thing is they exist like single or maybe as together as a clusters. So you can see bacilli, cocci, and spiral shape. There are different organisms. Are bacteria alive? Yes. What does it mean? They reproduce, they need energy. How do bacteria reproduce? Here they mainly grow in number, not in size. Humans grow in size from child to adult. So they make copies of themselves by dividing in half. So you can see how they divide. How bacteria get energy? As I said, they are alive, they require energy. Some make their own foods from sunlight, like plants. Some are scavengers. So they share the environment around them. Bacterium in our stomach are now eating what you ate for breakfast. Some are warriors, or term pathogens. They attack other living things. Bacteria on your face can attack skin, causing infection and acne. So they consume tissue parts, tissue materials. Morphology. As said earlier, shape, different shapes and different in arrangement. Said earlier, bacilli, cocci, and spiral, and further, straight rod, club-shaped rods, branching rods, forms like vibrios, spore-forming rods, spiral forms, coccus. In the coccus, it divides in one plane, arranged in two, stem diplo by diplococcus. If they grow in one particular chain, angle, or dimension, it's a chain. They divide into two planes, so you can see bidirection. So it may be tetrad, quadrat likewise. But if they divide in all three planes, you can see as clusters. Known example is staphylococcus. Arrangement of cocci, single coccus, diplococcus in the cluster, staphylococcus. Usually streptococcus, it's in one direction or one dimensional application or division leads to chains like capitals. Here it is, imagine is three dimensional. It's like a grape-like cluster. Bacterial cell structure. I think now you're familiar with them. So from outer to inner, there are term fimbriae. You can see fimbriae, pili, flagella. So flagella. Then capsules. Not all possess capsule. And cell wall. All the bacteria are in cell wall except few. Then the plasma membrane. Then the cytoplasm. There are some inclusion proteins as granules and spore. Not all possess spores. And chromosome, so DNA, circular or cyclic arrangement is circular arrangement is there, not like being sophisticated to develop like eukaryotes. These are prokaryotes. Further in three-dimensional, you can see the inclusion granules, bacterial chromosome, or nucleus, or nucleus. Likewise, in the gram-negative cell wall we further discuss in later. Villi. They are short protein appendage, smaller than flagella. Main advantage is they possess villi, so adherence of the bacteria to the surfaces. As we discussed in the earlier lecture, post-microbe interaction. So adherence is one major factor. So villi, so multiple villi, adherence is high. At the same time, body produce antibodies against these villi. So adherence will be interrupted if it is immune or early infected, early colonized. Other important is F pillars. So it is involved in conjugation. It's a part of exchange of genetic information. So there are three ways: transduction, transformation, and conjugation will be discussed in upcoming lecture. And also it is involved in flotation. So they can float in water. So they survive oxygen on surface. They can float in. So pili, the helpful device. Flagella. It's a large one. It helps to motility or the movement. So different bacteria possess different form of motility. So in Proteus, they're swarming. It's termed swarming motility, like a wave. You can see the practical. And depending on the arrangement of the flagella, we classify bacteria basically in four types. Monotrichous, that is only in one A. Other one is lipotrichous, that is tough one A. There are several. Then amphitrichous, that is amphitrichous, that is both ends. If it is peritrichous, it's all surrounding on the three dimension. That's all. So there are a few examples. Depending on their flagella location, their motility type is different. So these are few motile bacteria. So about the bacterial cell wall, it helps to determine the shape of the bacteria as focus as the bacillus like or spiral. Also, it prevents osmotic rupture. So it strengthens the cell support, determine the shape of the bacteria as well as prevent from the osmotic rupture from outside. All but clinical application is some antibiotics affect directly. Some means the major one, penicillin, beta lactams, they act mainly. Cell wall. It made up of peptidoglycan polymer. It's made up of amino acid plus sugars. N-acetyl glutamic acid, N-acetyl muramic acid. Those are the sugars. So it is bound with amino acids. NAC and NAM bound with amino acids. So that is the peptidoglycan polymer. It's a polymer. So all the bacteria are encased in the cell wall. So it's a major polymer is the peptidoglycan. It provides strength, rigidity, found only in bacteria. So in gram-positives, there is a thick peptidoglycan layer. Gram-negative compared to gram-positive, the thickness is less. But sandwich between outer and inner membrane. There are two membranes in gram-negatives. You can see here, this is a gram-positive one, thick peptidoglycan layer and plasma membrane. Here it is outer membrane is there, then thin peptidoglycan layer is there, and this is the inner membrane. Inner membrane and thin peptidoglycan layer turn periplasmic space. It's a sandwich line. Two membranes. In the center, there is a thin peptidoglycan layer. Other than that, there are protrusions and influx mediating channels. It's termed pores. Protrusions are, this is simple like lipopolysaccharides, those things. But pores are the one which penetrate to the cell wall. These are very much important regarding antimicrobial penetration. So imagine this is a cross section, but imagine this is the outer part, this is in the cytoplasm. So my antibiotic should, once it reaches to here, it should penetrate cell wall to reach the cytoplasm. If they act on cytoplasm, these must penetrate. Even to act on the peptidoglycan layer, cell wall, they need to adhere, penetrate like this. So for that there are channels. It's termed pores. Specifically about the gram-positive cell wall, I said in endotoxins. Most of our endotoxins, gram-positives, gram-negatives, cell wall constitute. Once these bacteria colonize in our surface of body, immune cell will come and act on them. So it leads to damage or destruction. Following the destruction, these molecules liberated into our body circulation. So now it acts as toxins. They provoke more inflammatory response. That's why they turn toxins, endotoxins, leading to toxemia. So specifically in the gram-positives, there are termed lipoteicholic acid and teicholic acid. Teicholic acid which bound only to the peptidoglycan layer. Lipoteicholic acid which originated from the cell membrane. But teicholic acid and lipoteicholic acid are confined to gram-positive cell. Compared to lipopolysaccharides, LPS, they are in gram-negative cell. So all are termed as endotoxins. You can see about a bit more about three-dimensional orientation of this. Here cell wall, all teicholic acid is there, how the peptidoglycan there, the gram-positive cell membrane, cell wall, plasma membrane is there. Here in the gram-negative, two cell membranes are there, bound by thin peptidoglycan layer. There are lipoproteins, phospholipids, enzymes, and active substance. You can see the pores of proteins, plasma membrane, receptors, like this. Further, in the gram-positive, teicholic acid, gram-negative, lipopolysaccharides. So there are key differences and similarities, but compared to gram-negative cell wall, gram-positive cell wall, peptidoglycan thickness is very high. And it contains cell wall 90% of by peptidoglycan. Here in the gram-negative, it is 5 to 10%. It contains teicholic acid. In gram-negative, no teicholic acid. It's a single layer. It's a monolayer, but complex, but much more complex, three-layer outer membrane, cell wall with a thin peptidoglycan layer, and inner membrane, like this. Not many polysaccharides in gram-positive wall, but gram-negative, there are much more. There are other exceptions not related to mainly every bacteria. There are so-called acid-fast cells which contain mycolic